totally network. The network is just bad and it's not working. And then you talk to networking people and say, no, network is fine, you're good, carry on. There's something wrong with your devices. We kind of started iterating around that, and we said, well, what if there is a way to prove that both of you are wrong? Both of you are right. It actually is the network, or it's not the network. Or how do I also know in advance that my network is going to support whatever I'm trying to actually build on top of that network? So as we progress into more and more wider commodity level adoption of high performance IP streams, suddenly a lot of people are starting to build those huge data center grade networks. Or maybe you're actually trying to retrofit some of your smaller switches to do something very, very high performant. And then you start getting into this discussion like, okay, is it really a network? Is it not the network? And as you may know, that the ST2110 actually has a very strict requirements towards the network. And you shouldn't really load it to a certain point, and then you run into these weird problems that's really hard to troubleshoot. And so we thought, how can you test that in advance? When you create a POC, when you design your system, how can you know and calculate? Well, there are ways to calculate, but then we also encountered some scenarios where it's kind of predictable, but it's also not. And then the theoretical calculation of, okay, I can probably run this many streams on this switch platform. Suddenly it gets thrown in the window because some real world performance or some particularities of a particular switch platform, how they implement the buffers or the switching mechanism, can then play a role in all that. And then we started to look into tools, and we realized that in order to kind of just test that in advance without putting all of your media flows into the network, that's going to be some many thousands of dollars in very expensive, again, enterprise and data center grade equipment. And then we thought there should be a better way. And so we started looking at the open source tools and some off-the-shelf components to basically build that you can put into your system before you load it, so that you know that the network that you've designed will be able to sustain that kind of load on an extended period, and that suddenly your traffic pattern that Willem will be extensively talking about in a minute will not go somewhere sideways because you've just introduced one more flow. So we basically took an off-the-shelf server with the latest AMD EPYC platform. The reason for going with AMD EPYC is just an enormous number of PCIe lanes that are accessible directly on the CPU. And we just loaded it with the ConnectX 6 and ConnectX 5 cards. We specifically picked various cards that you may be having laying around from some previous projects, some ConnectX 5s, ConnectX 6s from different generation with PCIe Gen 3, Gen 4. And relatively, compared to some of the tools that I mentioned, relatively inexpensive platform that you can just load with those cards and say, can you please just put everything that you have into the network? And so we selected the tool from Cisco Systems called T-Rex. It's an open sourced traffic generator that they're using on top of the DPDK, which is the typical networking API that bypasses the Linux kernel and just enables. It just gives you the ability to use the ASIC on the network on the NIC to just generate whatever traffic you want. And then, yeah, of course, the T-Rex is an open source platform for that just gives you a nice kind of API and nice GUI on top of that. But the cool thing about the T-Rex that we also going to talk a little bit in a moment, Willem will take over from me, is that you can actually put in the profile of the traffic. So you can basically say, I don't need a generic internet-style traffic because that's not what I'm going to be using. I'm actually going to be using a huge loads of multicast RTP traffic. Can you please replicate this kind of behavior into the network? And in fact, this thing can. And so, Willem, would you like to talk a little bit about it?
Okay, so very cool. system. Now we need to have load into the network. So we thought about, well, synthetic payload, right? That's pretty easy. That's just a bunch of data that you give into the packets and off we go. Now, if we look into the type of payload that we should be using in a traffic generator, you could look at a typical data center. And typically there are what they call, which are continuous big data streams. I'll grab the microphone a little bit closer. So those are big data streams, just like video. So you could compare it to this. And there's also the notion of mice streams, which are very tiny streams, maybe not continuous. You can think about ancillary data or audio that's continuous, but also a very tiny stream, right? So synthetic payload, at first, I think that's a good start. So if we look at our profiles, we have audio, typical bitrate 1.5 megabit per second. Ancillary data, it can vary. It's sometimes much lower than 1.5 megabit. And then there's the video, of course. That's the 1080i/25. Typically 1.1 gigabit per second, and if you move up into the tree, that's 2.2 gigabit, and for UHD, around 10 gigabit per second. So this is the ballpark that we need to have and to be able to stream. Now, at this point of the paper, we don't look into something that we call out as the traffic shaping profile, like 2110-21, and actually we should. And a very small calculation brought with me. Sorry for the mathematical details, but the important thing is there is a traffic shape. And it's not just about pacing the packets along the whole frame. No, there's also something called the gap. So let's do a very small overview and say, let's say we have a 1080 I/25 video, 4:2 color and 10-bit. Then we can do a small calculation. At the end we say, okay, this stream is 1.106 gigabit per second. So if we have a 10 gigabit network and we want to test drive this, we can put 9 streams through the network and it should be okay. Now, I can tell you it's not okay. The reason for this is actually the read shuttle, the gapped packet read shuttle. So this means that for each frame, there's a smaller amount of time to send over all the packets. So the gap actually, well, there's no packets, but actually you should count the gap as being useful. So if we look at the gap, that's approximately 4% of the whole frame, and we add this to the bandwidth, then we see 1.151 gigabit. Small change, but now suddenly you see that you're only capable of sending 8 streams, because we did a test at a VRT lab, and we saw that just pushing 9 streams to a network, it works perfectly. You don't drop any packet, but the problem is you don't have the bandwidth to preserve the gap. So all the packets seem to be smeared out, and you have a linear packet shuttle suddenly. This means that if you're just putting in some traffic and you don't think about the gap, you don't know enough about your network. So in future work, we need to take care about this detail as well. So yeah, you can push 9 streams, but it won't work. So the packet, the traffic shape will be changed, and as a result, the receiver will have too much packets at the moment in time that it doesn't need to receive packets. So the ingress buffer of the receiver will be overflowed. And there you go. It doesn't work for the receiver. So, of course, then you go into platform testing. And this is probably where I hand the mic back.
Thanks, Willem. So now we're going to talk about the software, the testing, what we did in the actual platform itself. So we basically started off, as you saw from the presentation in the beginning when Ievgen was explaining the platform, we have one of the nice things about the AMD EPYC architecture we're using is there are a lot of PCIe lanes directly connected to the CPU. So that was one of the reasons why we chose that platform. And for the purpose of the testing, we decided to start off with a baseline of using 4 different NICs. And in this case, we were using the ConnectX-60X and the 5, so 2 different generations, because again, the purpose here is to explain that it's an open platform. You can use different pieces of hardware, different generations, things you maybe have, or if you need latest and greatest, you can use ConnectX-7. And the way it works is we're running in what is called loopback configuration. So we're just doing from one port, these are dual port cards, from one port to the other, but we're looping the traffic because for the purpose of the testing, which is the phase 1 of this project, we wanted to verify how much data we could actually produce out of this platform under what load. And therefore, we configured T-Rex in order to simulate 400 gigs of traffic. We've got these four NICs. 4 of the ports are therefore outputting at 100 gig, and the other 4 ports are receiving it. So we're just verifying that we can actually physically load this. So 10 seconds of history. T-Rex is a project that's been out for a number of years. And back in the day, if you look at the original documentation, they were more or less talking about how do we get 10 gig working out of the platform. So obviously now we're talking about how do we get 100 gig and how do we get multiple 100 gigs. So the documentation still refers to 10 gig or in that space. So the results that we achieved were, well, not exactly what we'd hoped for, but that's the whole purpose of this project, is to demystify and understand what are the limits we can reach. So we're able to reach around 385 gigs of traffic on here, and the ramp loading takes about 10 seconds from the moment where you actually start the YAML script where you've configured your parameters to when you have the full load. But what's interesting is we've only have 7% of CPU utilization. So we definitely believe that that's not the bottleneck. The bottleneck, why we can't achieve line rate, is maybe buried in our configuration parameters or elsewhere. So this is just a screenshot of the output of the software whilst it's actually running. So you can see CPU utilization, I said, around 7%, 384 gigs of TX and RX. And the other thing also is that we're trying to make sure that we're not dropping packets. So in the original test with the 4 NICs, it was pretty good for what we were trying to achieve. So then we decided that we would actually load it with an extra 2 NICs. So first of all, we're stretching a little bit the architecture because we're now running across multiple NUMAs. So we have different CPUs that have different memory groups that are assigned to different PCIe lanes that are assigned to different NICs. So normally when you run these multi-threaded, multi-CPU architectures, you try and make sure that you're matching your memory with your resources and your CPUs and your I/O, in the NIC in this case. So we added the 2 extra NICs, and we had them across these 2 risers in the system across the 2 different NUMAs. And we were trying to reach, obviously, 600 gigs of traffic, again, with the same loopback model where we've got one port going to the other just to verify that we're actually getting the output that we're looking for. So here we had around 582 gigs of traffic, but we started to notice that we're getting some errors. So you can see that the non-zero total queue full counters, it's a bit of a mouthful, we started seeing that above 560 gigs of traffic, that started to build up slowly. CPU, on the other hand, is still around 7%. So again, we believe that the problem is not the bottleneck in the CPU, but maybe how the software is configured, the architecture, the fact that it was designed, maybe not originally to perform at that rate. We're still investigating. That's the point we're saying. So here you actually see the output again. So 582 gigs of traffic. You've got the expected, and you ultimately have, again, around the 7% CPU. So what do you do next? You're in this multi-CPU architecture. One of the things you typically do in these environments is you want to pin all your processes and you want to manage everything. So in AMD's world, it's called SMT, the simultaneous multi-threading. Allows you running multiple threads on the same given core. We wanted to disable that. That's usually something that you do in any of the core pinning environments. You don't want anything to be dynamic. You want to be in control where your processes are tied to what I/O again, what NUMA, but really nail it down. So for this round, we actually disabled SMT, and we were, hoping that it would improve the performance of what we're doing. But what was interesting is actually we were seeing slightly less good results, which for the time being, based on the amount of time we've had to work on this project and the publication of these slides, we have not come to the conclusion as to why this is blocking yet. But it's in the investigation stage right now as to why we are getting a decrease in performance when the fact that we are nailing processes to specific resources should in fact improve the performance or at least be equal, all things said. So this is something that we're looking into. Why do we see in the 20-second test that we're doing that number of packets, but the number of errors with and without the core pinnings? Another important part of the testing that we're doing is we need external validation. It's very nice that the application tells us that it's sending this amount of traffic and it's receiving the same amount of traffic. All good. So what did we decide? We'd do a very simple test. We would connect it to a 100 gig capable switch from any vendor who can provide such capacity at non-blocking rates, obviously. And in this case, we did run it through that switch because we wanted to verify that the switch would identify the fact that the bandwidth that is being sent by these NICs via the T-Rex application was actually the bandwidth that's being measured on the receive side, in this case via the switch. So the whole goal there was just to verify that using the different DACs that we were running at 100 gig, from the TX to the RX, we were achieving the performance that was expected. And here you can actually see the output of said switch, where we see the expected output rate, which matches the rates that you saw on the previous slides, at which we'd configured the T-Rex in order to perform. So we're not 100% line rate. Obviously, it can be based on gap, it can be based on packet distribution, it can be based on a number of things, but it is in line with transmit equals receive, which was the important validation we were looking for at that point in time. And with that, I'll hand it back to Ievgen.
Thanks, Thomas. Thanks, Willem. So, to conclude, we think that the initial results of our testing with the first phase of this project are promising, that we should be able to build these sort of open source, open hardware, open software performance validation tool for the use at broadcasting or at installations anywhere that you need to test, load test the network performance, and using off-the-shelf equipment that really allows you to be flexible with the budgets or with your goals or with the kind of performance that you need to test. And we're confident that we can use the synthetic payloads, and that's actually going to be the point of our future work, because the next phase of the project will be to talk to the broadcasters who are currently running large-scale ST2110 installations and gather that statistical data of what kind of traffic patterns are running through their network in order to build this as a profile and then publish it as a industry recommendation with one or another bodies. We also would like to look into the questions of synchronization of that testing platform and to see how impactful locking it to PTP will be to the pacing of the generator itself, and whether that will be a big difference, and how actually also the PTP locked network will react to all that. And as the last phase, at some point, we plan to publish it as a guide of how to use both pieces of the puzzle, the platform and the traffic pattern, how to use it to test these sorts of networks at scale and at capacity. So with that, any questions to either of us? Hopefully it was interesting. Thank you.